In 2012, American theoretical physicist John Preskill introduced the term quantum supremacy to describe a scenario in which a quantum computer can solve a problem that no classical computer, not even our most powerful ones, can solve within a given amount of time. It all started in the 1980s when Richard Feynman, a renowned physicist, proposed the idea of quantum computing. The concept caught on, and very soon the race for quantum supremacy was on, even before the term quantum supremacy was coined. For many years, this idea was considered possible only in science fiction. But recently, tech giants like Google and IBM have claimed to achieve quantum supremacy. Well, there was a bit of controversy regarding the term supremacy in the Western market, but the success of quantum computing can push the modern world towards technological advancement and maybe even singularity, like we explained in this video. So today, let's understand how exactly do quantum computers work and what makes them so different from classical computing. My name is Siddharth, and you're watching The World of Science.
I have little doubt that we'll be able to produce machines and computer programs.
There's this quantum world out there, and it somehow has these extraordinary resources
that will behave in a fashion that we speak of as intelligent,
which are much different from any resources we encounter.
What's going to happen to us all tomorrow? Who's going to be in charge, machines or men?
In 2019, Google produced a 53-qubit quantum processor known as Sycamore, which performed an incredibly complex simulation in merely 4 minutes, which, as per their claims, would have taken nearly 10,000 years for a classical computer. To give you a perspective, a 53-qubit quantum computer would be equal in terms of processing power to a conventional computer, which is running at 16 teraflops. That is 1.6 trillion floating points operations per second. Now, the latest version of Sycamore has 70 qubits, which is a significant increase from 53 qubits of its earlier version. Sycamore used superconducting circuits which cooled them down to nearly absolute zero temperature, where electrical signals started to behave like quantum mechanical signals. Okay, let's just hold on here for a second. I've used too many technical terms like qubits and superconductors and quantum mechanical signals, etc. Don't worry, we'll just break it down for you. Before we go to quantum computing, let's just understand the basics of the computation process. A computer is called so because it performs arithmetic and logical operations in its central processing unit. Every piece of data in the computer exists in the form of binary digits, that is, zeros and ones, which pass through logic gates to deliver the appropriate output. A computer is made up of microprocessors, which consists of transistors and integrated circuits, or ICs. Now, the function of these transistors and ICs is switching operation, that is, on and off, or mathematically 1 and 0. Now, these data are stored in storage devices and are used for temporary and permanent use using electrical signals. For example, you see this image? The computers encode each pixel of the image you see in terms of zeros and ones. One way of representing color in the computers is in the form of RGB notation. To represent the range of values from 0 to 255, each color channel is typically allocated 8 bits, that is, 1 byte of memory. This allows for 256 possible values for each color channel, which is sufficient to represent a full range of intensities from 0 to 255, where 0 is no intensity, black, to maximum intensity 255, full brightness. The binary values for the red, blue and green color are combined to form a single binary number which represents the color of the pixel. For example, if the red channel is 128, the green channel is 64 and the blue channel is 192, the combined binary representation would be 1000000000 01000000 11000000. These combinations of a long sequence of zeros and ones produce an image pixel by pixel. So, to perform any operation on a computer, we need a long string of zeros and ones, a processor to check and process information, some storage space to store temporary values, and a lot more other things. Now that we have understood the basics of computing process, we can move ahead to understand quantum computing. As we saw, classical computers operate with only two values, 0 and 1, and rely on predefined physical states to perform calculations. On the other hand, quantum computers perform calculations based on the probabilistic states of an object before it is measured. This allows quantum computers to process exponentially more data than the classical ones. The zeros and ones in classical computing are called bits, while a quantum computer takes the data in form of qubits or quantum bits. It defines the quantum state of an object that is neither predefined nor detected before measurement. Unlike classical computers, which can only take one value at a time, quantum computers can take multiple values simultaneously using the superposition principle of quantum mechanics. At the quantum scale, particles exist in terms of superposition, meaning they can exist in all possible states at once until they are measured. For example, an electron may have spin states that can point up or down depending on its alignment with magnetic field lines. However, we can only know the spin state of an electron at a specific time after it is measured. Another example is the double slit experiment, which shows that an unobserved state produces an interference pattern, while when a measurement is done, two distinct bands appear on the screen. The spin state of electrons and the polarization state of photons are examples of quantum objects that can be used as qubits. Unlike classical computers, an electron can possess both values 0 and 1 simultaneously. Quantum entanglement is another principle of quantum mechanics which allows superposition states to entangle with the system, producing complex mathematical relations for the final outcome when measured. These complex mathematical relations, when put together, form algorithm, which is what a quantum algorithm is. But why the do we need quantum computers? Well, there are problems that require extensive calculations, and for that, scientists use supercomputers. For example, modeling the behavior of an individual atom in a molecule requires considering thousands of interactions, and that requires a large working space. Another example is the study of protein chain foldings in complex shapes. A long amino acid can fold through infinitely many ways, but that makes it a huge problem for classical computers. Quantum computers will use quantum algorithms that will create multi-dimensional space to find the best way to use the least possible energy. Quantum computers are not just fast in processing, they're also compact in size. Quantum computers, along with their hardware, are generally the size of a normal car, with a majority of the area consisting of a cooling system to keep the processor super cold. The supercharged refrigerator uses liquefied helium to maintain the temperature near absolute zero. Now, as we know, when the temperature reaches near absolute zero, conductors start to act like superconductors. At such a low temperature, electrons will form a temporary bond with other electrons, forming a Cooper pair. This Cooper pair moves within the conductor with almost zero resistance, and thus the phenomenon of superconductivity arises. These Cooper pairs can carry charges across insulation barrier. We call this quantum tunneling. Using this phenomenon, an arrangement is made where two superconductors are placed on either side of an insulator. This junction is called the Josephson junction. By the way, this Josephson junction is also used by quantum computers as qubits. We can send microwave photons fired at these qubits and control their behavior. Here, the photons are made to hold some quantum data, and this quantum data can be manipulated and read out. Quantum information in superposition states contains all possible configurations of the qubit. As a quantum computer can use 0 and 1 simultaneously, it contains all four possibilities 0, 0, 0, 1, 1, 0, and 1, 1, unlike the classical computer that can use only 0 or 1 at a time. When many groups of qubits in a superposition are arranged together, they form a complex multi-dimensional space which is used for fast data processing. Okay, so quantum computers can store more data than classical computers, perform computations faster, and have more computational space. However, there are certain challenges with regards to this technology. We know when a quantum particle comes into contact with an observer, its superposition breaks, resulting in a single state known as wave function collapse. This is the main problem with a quantum computer. When the superposition meets the measured state, it loses its coherence, creating a state called decoherence. To address this issue, we need to shield the quantum state of particles effectively. Tech giants like IBM and Google are racing for quantum supremacy by developing such solutions. With Google, IBM and China on the other side claiming quantum supremacy, the possibilities in the field of technology are endless. The future of quantum computing will see the development of more complex quantum computers capable of performing bigger calculations like the ones required to solve the problem of singularity or overcoming the challenges of string theory. Quantum computing represents the pinnacle of human technical achievements, making the future full of surprises and excitement. So, what's your thought on quantum computing? Let us know in the comments. If you found this video interesting, please share it with your friends. Make sure you subscribe to the World of Science. Until next time, stay scientific.